Alright, welcome to video number 3, the last video of this unit. In this particular video, we're going to take a look at the difference between 3 different terms, and I've got them right here in the video. I've got forced vibrations, natural frequencies, and then a term that you've probably heard of before, but maybe not know exactly what it is, and that's resonance. So we want to know the difference between, when we're done with this video, we want to know the difference between forced vibrations, natural frequencies, and then resonance. And I've got a couple examples that I'll try to demonstrate on the video, and keep in mind, any demonstration I do on a video, you are more than welcome to do on your own in class, and that's totally cool because science is all about you doing it, not just me doing it. So here we go. Alright, we're going to start with forced vibrations, and I think I'm going to start off with a demonstration real quick, and then I'll fill in the blanks. And my demonstration comes from tuning fork that I have right here. I'm going to go ahead and try this. I don't know how well it's going to come across on the video, but I think you've seen this demonstration before, so I think when I do it, if you can't hear the demonstration, I think that might trigger your memory, and then you go, oh yeah, I've seen something like that before. And if you haven't, then by all means, when the video's over, you get a tuning fork and you do it. As a matter of fact, you're going to have to do it anyway because that's part of the packet. So here it is. So I'm going to basically have a tuning fork, and I'm going to strike it. Okay, and there it is. And all I'm going to do is just take the tuning fork and put it right on top of the table. And instead of the tuning fork vibrating, I'll have the tuning fork, and then the tuning fork will make the table vibrate as well. And so here it is. Now, I don't know how well that came out, but what happened was, since this tuning fork was vibrating, when I put it on the table, it causes the entire table to vibrate. And if the table vibrates, since the table's bigger than the tuning fork, it produces more sound and it gets louder. Now, I'm not sure if that came across on the video, but what we call that is, we call that a forced vibration. We're forcing the table to vibrate at the frequency of the tuning fork. That's all it is. Very simple. Okay? And so it's a forced vibration. And if I had a different frequency fork and I struck it, the table would vibrate at that particular frequency of that fork. So there's no special frequency that the table will vibrate at. It'll just always vibrate at the frequency of that particular fork that is connected to it. So let's fill in the blanks. Forced vibrations. This is the vibration of an object that is made to vibrate by another vibrating object that is nearby. Okay? A sounding board in a musical instrument, like a guitar. The strings on a guitar, okay, if you just had the strings and you didn't have the wooden base to it, you wouldn't hear let's say hearing the strings vibrate would be nearly impossible. But when the strings vibrate, they make the whole guitar vibrate. And when they make the whole guitar vibrate, since the guitar is bigger than the strings, then you can hear it. The body of the guitar, the sounding board of the guitar, amplifies that sound. You can hear it. So that's why they make those out of wood. And the wooden body then amplifies the sound, and they call that a forced vibration. So the strings of the guitar force the body of the guitar to vibrate at very loud sounds. So the sounding board in a musical instrument amplifies the sound through forced vibrations. If a guitar did not have a wooden body, which is called a sounding board, the sound produced by the string would not be heard, or be very difficult to hear. The vibrating strings cause the body, that's the wooden part of the guitar, called the sounding board, to also vibrate. This forced vibration amplifies amplifies the sound by making it louder. Sounding boards, such as guitars, can be made to vibrate at nearly any frequency. Woo. And that's key. That one's key because that's going to distinguish force vibrations from natural frequencies. So, natural frequencies, here we go. A natural frequency, a frequency at which an elastic object, once energized, remember elastic object is something that returns back to its original shape. That would be like a tuning fork, because when you strike it, it vibrates back and forth, always goes back to its original shape. A frequency at which an elastic object energized will vibrate. When any object composed of elastic material is disturbed, it vibrates at its own, this is real important, natural set of frequencies, which together form its special sound. So this is a force vibration. As soon as I strike the tuning fork, that sound you hear is characteristic of that particular fork. Now, I can force those sounds into the table by putting it on the table. Those are force vibrations. But if I just strike this guy here, it produces its own vibrations. And those vibrations, if I want to, which are natural frequencies, can be forced into the table itself by touching the two together. So an object's natural frequency depends upon factors such as the elasticity of that object and the shape of the object. So its elasticity and shape will affect what its natural frequencies will be. Most objects, they have springiness to them. That's kind of another way of saying elasticity. From atoms, actually atoms have springiness to them, and whole planets can actually vibrate. Will vibrate at one or more natural frequencies. What are some examples? Examples of common objects that have natural frequencies include, you've seen it already, tuning forks, okay? Another one, bells. Okay, so if I strike a bell and you hear that characteristic sound of the bell, that's a natural frequency. And then the other one, which you're going to do here in a bit, are wine glasses. Okay, and that's kind of cool, and it's a neat demonstration. All right, the last one is resonance. All right, resonance is this. It's a phenomena that occurs when the frequency of a force vibration on an object matches, and that's the key word here, matches the object's natural frequency, and a dramatic increase in volume and amplitude results. So it's those two blanks there are volume and amplitude. All right. Quick example of this. I'll talk about it, and then you'll do one a little later on as a lab. But if I have a tuning fork, and this tuning fork is labeled as you can see it right there, 512. That's 512 hertz. Okay. Which is the musical note C. If I have two tuning forks, and both of them are 512. And if I strike just one of them, and I put the other one next to it, I don't even have to touch it. If I put that other one next to it, these vibrations will actually cause this one to vibrate. So I can strike this tuning fork, this one will begin to vibrate, and then I'll have both of them vibrating. That's what we call resonance. Okay, and I think when this video is done and we have a chance as a class, we'll talk a little about resonance as a class, because it's kind of a tougher concept to illustrate and talk about and demonstrate. on video. So let me just go ahead and give you the last bullet, or last bullet point, and last blanks, and then we'll let you move on. So here it is. Examples of resonating objects include wine glasses. I mean, there's a lot of examples. These are just a couple. Bridges. We'll talk about that together. Remind me to talk about that as a class. And pipes. And you're going to do a lab on pipes, and you'll have a better understanding of what resonance is after that. Good luck on the rest of the unit.